Hello everybody, and welcome to my channel. Today is February 22nd of 2022, and my name is Steve Matthews, known also as Teeth of the Lamb, and today we're going to talk about some interesting observations. I've titled this video The Suns Toroidal Field and Why a Crescent Moon Has Earthshine. I'll dedicate about half of this video to each topic, and first up will be the Suns Toroidal Field and the evidences that I believe may support that theory. And these are just my thoughts and my observations, and you can weigh them out and decide for yourself what you think. So I'd like to start this off with two quotes from Scripture. First, Romans 1:20. For the invisible things of him from the creation of the world are clearly seen, being understood by the things that are made, even his eternal power and Godhead, so that they are without excuse. That may be appropriate to what we're going to observe today. And then Psalms 19:1. I believe this is on Warner von Braun's tombstone. The heavens declare the glory of God, and the firmament showeth his handiwork. In this video, we're going to assume that we are on a flat, stationary, non-rotating Earth, and that the realm that we are in is an electromagnetic plane of existence, which we call our home, Earth. And that the sun and the moon and the stars revolve around over our head in a circuit. I didn't always believe that, but over the past few years, I've looked at the preponderance of evidence, and it indicates that we are indeed on that flat plane. And so I'm going to base everything off of that and these observations and what they mean based on that conclusion. So since I mentioned Earthshine, I'd like to take a moment and just tell you what it is. We're not going to actually cover that right here, but it'll be on the second half of this video. Earthshine is when you see a waxing or waning crescent moon, and you can see a faint light on the dark part of the face of the moon. So as we move on to our first topic of the Sun's Toroidal Field, I just want to say that what we're discussing here is nothing more than just a theory. So it's on par with that of NASA and Einstein, who are the theory kings. So I'd like to just mention 6 of the topics that we're going to look at that support, in my mind, that there is some sort of a toroidal field around the sun, and it's evident at sunrise and sunset. Number 1, sun rays shining upward. Number 2, when you look at the sun as it's setting on the horizon and you pan right or left, the light becomes notably decreased as you move away from the sun. Number 3, as you look at the sun when it's on the horizon, you can see a notable V-shaped pattern of light coming out of the top of the sun. Maybe that's the vertex of the toroidal field. Number 4, the underside of clouds lighting up by a sun that has never diminished its altitude in reality. Number 5, brilliant and sometimes spectacular shows of light in the atmosphere, as if the light molecules have become agitated. Number 6. Right after the sun starts to rise, you can see on the opposite horizon sometimes an equally splendid display of light and color on the clouds and in the atmosphere. I don't know what that's called, but if you're looking for all the scientific names and stuff in this video, you won't find it. But you will get my observations, and you can add all that stuff to it, all the terminology. Let's take a look at how big this field would be and what the field would look like if you were to draw it out, since you can't really see it with your eyes, but you can see the evidence that it's there. It's stated that at the equator, the circumference of the Earth is 24,901 miles. Again, going at the equator, let's assume that the sun actually lights up half of the Earth at a time. That would be 12,450 miles between sunset and sunrise. Since a toroidal field is assumed to be usually round, donut-shaped, let's divide that 12,450 miles by 2, which gives us a center of 6,225 miles. So at the moment of sunrise or sunset, the sun would be approximately 6,225 miles to the center of that toroidal field. So at the moment of sunrise or sunset, the sun would be approximately 6,225 miles away, 1/4 of the distance around a 24,901 mile Earth. At the moment of sunset or sunrise, we're at the outer reaches of light on the outer perimeter of the toroidal field, and light is pulled up and returns back to the vertex. You have a north and a south on the toroidal field, and so when you're on the outer perimeter, the light is being pulled back upward to the other field. In this diagram, you would be standing where the blue dot is, at the outer reaches of the field. What I'm trying to say is how a toroidal field works is there's a north and a south pole. And you see the blue dot in the lower left-hand corner? At sunset, you're exiting that field. And so you would be like where the blue dot is. That's why light rays are pulled upward. And you get the underside of the clouds lit up, and you see light rays going up from the sun. And these return from back from whence it came, the light rays. They exit out from the bottom pole, and they go out as far as they can reach, and then they're pulled back to the upper pole. And I don't know which one is north and which one is south, but that's something that can be talked about. But it explains why we see light rays going up, and then also why the underside of the clouds are lit up. And when you're on the sunrise, you're entering that field. On the outer perimeters, when the light is pulled up to return back to its source, you would see a lot of agitation in the molecules, causing spectacular light shows of color. And it may also be partially responsible for some of the things we see in the aurora borealis. Looking at it from a side view, again, the blue dot in the lower left-hand corner would be where you're standing exiting the field at sunset, and the light rays are being pulled up at that time. And that's why we get at twilight a lot of weird anomalies. And you can see that the light returns back to the upper pole of the sun. Pay no attention to the arrows on this diagram, but I'm no graphic designer, so I had to use graphics that I could find online to demonstrate what I'm talking about. Those arrows aren't accurate. Here's a GIF that I found online of a torus that's used in harmonic resolution therapy and the HRT, where the vertex, the center, is folded back in on itself. And I don't know that that's what the sun's doing, but I thought it interesting and valuable to include a graphic to give you a visual of what a toroidal field looks like. Now let's lay it out on a flat plane to see what that field might look like. Start with a flat stationary plane and put a firmament above it and a sun, and we'll add a moon, and then we're going to put our toroidal field around that. The moon is in a crescent phase. It's inside of that field. Put some darkness, and then we'll put some arrows designating that the light is returning back to its source. And I think this graphic might serve some purposes here. And we've also got the light rays going around, kind of at an angle. So we've got the moon captured inside of within the reach of the light of the sun. And if you move that moon outside, I don't think you would have any of that moon earth shine that I was talking about. You only have that inside of that field. And you're standing outside looking in. And that only occurs during a crescent moon at sunset or sunrise. You don't see it during any other phase of the moon because you're too far away. But during a crescent moon, the moon is at its closest proximity to the sun. And so when you're on the outer reaches of the light, you can actually see it for a few hours prior to sunset. And when after sunset, you can still see it because it still hasn't gone out of sight due to perspective. And you're getting the reflected light from the returning light on the edge of that field, and also reflected light from the firmament above during the daytime. So you're able to view it while the moon is still captured within that field in the daylight. And it reflects just a little bit of light. And also, since you're standing in the dark, it works somewhat like a visor, which stops any reflected glare or anything from actual sunlight. And you get a better view, and we can see a faint reflected light on the dark portion of the face of the moon. I hope that makes sense. And why I've got this graphic on screen, I want to just elaborate a little bit about what I'm thinking is happening here. I think you get it already that the toroidal field, that the light exits the bottom pole and goes out and down and shines on the earth. But then as it reaches the outer limits, that 6,000 some miles away, light is pulled back around the field. And when you're at twilight, right on the edge of that field, light is being pulled up and back around and returning to the source. And then it enters into the top of the sun, back where it came from. And that's just a never-ending cycle. But in essence, when we see a sunset, the sun has gone out of sight due to distance and perspective, and it's all just a visual, optical thing. And in reality, that sun has never left its position in the sky. It's still at a high altitude. And the sun is, due to perspective and optics, it has gone down in the sky to where we can't visually make it out any longer. But at the same time, we're also at the outer limits and reach of light itself as we know it. Sunlight doesn't reach any further than the outer rim of that field, and then it pulled up and returns back to its source. And I think that is the way it's working, in my opinion. And I think the evidence we're going to go over here just shortly, and we'll lay that out even more clearly to you. We haven't really looked at the evidence yet. I've mentioned it, but haven't really laid it out. This is a good time to just have a little refresher on perspective. And question is, does perspective light up the underside of clouds? Cause light rays to flow upwards? Does it change the altitude of the sun or moon? Can perspective bring the stars down? Or can it rotate the moon? The answer to that question is no, it can't. What perspective primarily does is raises things and lowers things in your field of view due to the limitations of your own eyesight. It's not a real phenomena. It's only due to your eyesight. So when you look at those telephone poles there, the one at the end isn't any shorter than the ones at the beginning. They are all the same. And when you look at the sun, it's not really gone down. It's still at the same altitude it ever was. And that's important to keep in mind, that clouds, they don't get smaller as they go down toward the horizon. They're all basically flat on the bottom, hovering at one altitude. But they appear to go down because of your eyesight, the limitations of our visual acuity. And that's it. And it's called a vanishing point, where they meet the ground. And these are some pictures of some clouds that I took out at the beach when I was walking. Put it to good use. Think about this. Darkness also follows all of the laws of perspective. So when you see a sky that's dark like this, in reality, you're seeing darkness is pulled down further than it visually is. It's actually like this. And you might say, no, perspective doesn't affect the darkness. I'm saying, yes, it might. And when you saw the picture before this, it may actually be like this in reality, because darkness has to follow all the same laws that the sun, the clouds, the stars, the moon follow. What I'm saying is at least your visual perception of where that terminator line is misleading because of perspective. and visually it appears lower than it is in reality. That is the way perspective works, and it doesn't discriminate between one thing and another. But what actually causes the darkness is that you're at the end of the reach of light itself from that sun. And what makes me think that we live in a created realm or world is that when that sun hits that horizon line, is exactly at the distance of the reach of its light. And then it's pulled back, and that time period that light's being pulled back is called the twilight. So they both simultaneously happen. The sun reaches the horizon, its maximum distance for our visual sight, and the light is pulled back upward, back to the sun where it originated. Everything was timed exactly to match our visual perception, and it's timed perfectly. Tell me that's not a finely tuned machine. Watch what happens when the outer edge of the toroidal field passes by. Color is derived from light, and when the final bit of light is pulled away, you lose color because you have no light. And see, the final clouds, they dissipate, but it takes a little while for them to get to it because they're further away, quite a bit further away. Let's play it again. Here it comes. There goes the light and the color. Color comes from light. If you don't have it, you don't have no color. And there we go. What I think you just saw was the outer edges, outer reaches of the toroidal field passing by. Normally, we think of light as shining down, and most of the time it does, except when you get close to a sunset or a sunrise, then it shines up. And I think that's light returning back to the sun, changing its direction at the end of its limits. But see, these rays are going down, and sometimes you can see light going up a little earlier in the day, but usually always at sunset or sunrise. But here, what I think is happening, it could be one of a couple scenarios. But I think that the light is actually, you're looking at the field, and it's passing over you right now. You're right at the limits of it. And I think that those light rays are turning up on the edge of that field, and they're returning back toward the sun. And the reason they look like the sun rays are converging on the sun, you got to remember, it's like 6,000 miles away, and that perspective thing is still playing a big part in how these light rays look, but they're definitely going up. And I think they're turning up at the limits of that field and going back toward the sun. Again, that convergence is perspective because you're looking at a 6,000 mile away sun. And one of the evidences of that, why I think it is not only just this one thing, but we have also the underside of the clouds being lit up, meaning that light somehow is going upward. It's not coming down from the sun, because the sun, remember, due to perspective, it's still way, way, way up in the sky. It hasn't changed its altitude whatsoever. And that perspective thing is just a limit of our vision. Nothing has changed. In reality, the height's the same. And if that wasn't enough, we know that we're at the limits of that light. And and that sun is still at its same altitude, it should continue on for forever. Despite how we see, it should keep on continuing clear across the earth. Something has limited it, and I think that we're at the limit of the light, and it's turning upward and going back to the sun, because we're at the end of the light, and that means why did it change directions? It's going back again. And not very long before the sun reached this position, the light was shining down. Why has the light changed its direction? What has changed? The light's going up and going back. That light has made a 360-degree shift in the direction from down to up. That's got to mean something. We know we're on a flat plane. We're not looking at a 93 million mile away sun. 6,000 maybe, but not 93 million miles from where we're at. Here's another one. I have the little diagram in the lower right-hand corner, and I think because we're right in where that arrow is in the lower right-hand corner, that would be the turning point right at the dark, when we would be standing right there by that arrow, and light has changed and it's going up, and I don't know what that means exactly, but I think I know, and it's an interesting phenomena. I think the ballers are right, though. At the altitude of the sun, which is a realistic altitude and it never changes, maybe just a little variance to cause the phases on the moon, it should shine clear across this earth. But it doesn't because of the limits of its power and its field. Now when you look at this, excuse the graphics because I'm not good at graphics, but I think we're seeing the top of this field here. Now the light shining up, that's because you're on the edge of the field you're seeing the light go up. But it's going back and it's coming in to the top of the sun. These rays that are going up are actually the ones that are turning up on the edge of the field. And they're going back, and you see how it's darker on each side and kind of V-shaped on when you look away from look at the sun, and you kind of see a dark, it gets darker, and it's kind of V-shaped. I think it's going back into the sun there. The field that's the shape of the field. And that's just my thoughts. Don't know that it's true. Here's another one. And my line on the right-hand side should have been angled a little bit lower, but I'm not going to fix it. You get the idea. You can see that darker under the lines, it gets darker. And I think this is another example. You see it on all of them. And it means something, and I think it means that we're seeing evidence of the field, in my humble opinion. So here's another one, and you can see how it gets a little darker, but right above the sun, you've got that kind of V shape before it changes. It does a gradual change, but then it stays darker all the way out to the edge of the horizon. But I think the light is coming back in to the sun. It's like that. Yeah, it's just a theory. People may expand on it. So zooming in a little bit, here's another idea. This is how the field would be. And we're seeing that top of that sun, the V shape, where the arrows are. So here's another example. You see the top of the sun shining up here, but I think you're seeing the field as it moves away from us. And it may be bigger than this, but I'm just trying to get the point across, that we're seeing the light come in from right down into that hole to the sun. And everything around it is dark because the field's passed gone past us. And maybe that's right, maybe it's not. I don't know. I'm still trying to figure it all out. This is an oil painting that I made a long time back. And it was my first attempt at doing a sunset. But I remember that I desperately wanted to make the entire horizon light. And you just can't paint it that way because that's not what we see. And it looked odd. So I tried and tried again till I got it right. But if you don't make the dark on each side of it, it doesn't match reality. And on a ball, you would have the entire horizon or would be lit up by the sun. It would all be sunset. At least that's what I think. But you have to paint it in a focal light. You can't extend it out to the edges of the horizon. And it increasingly gets darker as you move out. So during sunrise or sunset, sometimes you can turn away from the sun, and on the opposite horizon, you see the clouds are all lit up, all brilliant, and almost as beautiful as a sunset. Now, this normally occurs after the sun has risen just above the horizon. And I think that those clouds that you see all lit up are where the edge of the field is, and the light's turning up still. And at sunset, that light is coming, the edge of the field is coming toward you. And so those lights, the light that turns upward, are affecting the color of those clouds. And I think that's the edge of the field. And it doesn't last real long. But it ends as it gets closer to you. And then you can't see that brilliance. Anyway, just another idea. So watch how the light moves away from you. And I think that's the edge of the field going out of sight. And it's the last remaining bit of light. Not all of it goes right on the edge. I mean, there's always light going back toward the source, all the way along the path of that field. But it's most condensed right at the edge of the field. And here it's coming toward you. And that field is getting closer. Now, if there was a lot of times it'll light up these clouds and make them all beautiful. And that concludes the Suns Toroidal Field. And now we're going to do, for just a few minutes, because I've already touched on it, why a crescent moon has earthshine. So one might say, well, the sun and the moon are up in the sky many times, and we don't see earthshine on the moon. But you got to remember that the moon is at its closest proximity to the sun. It's risen right around the same time as the sun, and sometimes it sets right around the same time as the sun during a crescent moon. And it's the only time that it's still within your visual range while you are on the terminator line. And normally the other phases of the moon, they would be up at the same time. Sometimes they come up they don't come up around the same time as the sun. They'll come up later in the day or earlier in the day, and so you can't see it. It's too far away because of perspective. The perspective has dropped it below the horizon for your eyes to see. But during a crescent moon, just for a few hours, it's close enough to that terminator line for you to still visually see it. And it's only up for a little while, then it sets, or it rises, with the sun, and you can only see it for a little while until the light reaches your position. The bottom line is a crescent moon is close enough to the terminator line, yet close enough to the sun, and the moon is in the light of the sun when you're looking at it, and you see a little bit of reflected light on the dark side. And any other time you can't see that because it's not in the light when you're looking at it. And when you look at the moon in the daylight, when the sun is up and the moon also, you can't see it because the atmosphere is too polluted with light. So it's only that short little time when you have fallen into the dark, yet the moon is in the light and within visual range. It hasn't set yet. And so you have that little time that you can see it and you get reflected light on it. In the daytime, the atmosphere is just too powerful. You could never see it. So I have another graphic, kind of a side view, that you can see that the moon is just over the terminator line. And I'm on the west coast of the United States, and the moon is getting close to the horizon. But I can see it because it's still in the light. I can see that reflected earth shine on the moon, and it's close enough to the sun also. So this graphic I used earlier. See, if the moon is outside of that field of the sun, of its light, then you can't see any shine on the dark portion of that moon. It's just black. But if you put that moon in the light and you're still within range, your visual range, then you'll see that light on the back side of the moon, on the dark side. It's faint light, but it's reflected light. And it could be from the light that's returning back to the sun, or it could be reflected light from the firmament. I'm not sure. So this is what I'm talking about. This is the so-called earth shine on the dark side of the face of the moon, and that's during a crescent. But this would be when it's still within that field of light and in your visual range. Any other time it's not. And you're not hindered by the atmosphere because you're standing outside of that field yourself, looking in. So I have a few minutes of footage that I was conducting a test to see what angle the sun has to be to produce that crescent. And if you're interested in watching it, I'll include it. The audio's poor, but I think you can understand. It ended up, conclusion, that the sun could not be below the moon to create that crescent. I have a camera setting on the table looking directly at it, and that's showing up in the lower right-hand corner. And then I filmed the whole process also. So you can't have a sun below the moon and create that crescent. It has to be about even with the moon. And that concludes my presentation. And that's my dog that you hear. You all have a nice day, and thanks for watching. My light is at the north right now. And I'm going to come around to the east. I'm going to go back to the west. Actually, northwest, and this is all the way west, right there. Come back. I'm northwest. Lights to the north. And I'm going to go northeast, and east. Now I'm going to bring the light down below the moon, and I'm to the east. I'm going to come around to the north, and I'm going to come around. I'm northwest, and now I'm west. Okay, I think the sun at this point is almost even, hold that there, almost even with the moon. Northeast and east. Almost at the bottom of the moon. Northeast, north, and northwest. I'm almost north. And northeast. Bring it up a little bit, so I'm about the same height as the moon. I'm at the northeast. Come around. Almost to the north. And northwest. And northeast. Kind of a little bit off of north. But I'm at the same height as the moon right now. And that's kind of what we see when we see the crescent, at least from my area. And it may be different in different areas, but never is the sun down here below the moon. It's not. Even though perspective and stuff makes it look like it is, it's not. I mean, the sun is usually set when the moon is still in the sky as a crescent. The sun has already gone down below the horizon. Due to perspective, though. Remember, we're not on a ball Earth, we're on a flat Earth. If I come up even with the moon, you get the crescent about right. Anyway, that's my test. And my camera is aimed directly at the moon. The camera on the table down here. That's aimed right at the moon. There's no. The only thing is it's at an angle looking at the moon, which when I see the sunset, the moon is still up in the air, so I have to angle my camera anyway. Okay, I will argue you cannot have the moon with the sun below it. Going to the south, going toward the north, and I'm going toward the west. I was above the moon, now I'm down even with the moon. I'm going from the west to the north. Now I'm going a little bit to the east. Okay, I'm going to go below the moon. And I'm northeast of it with the light. And now the light's shining from the north. Now the light's shining from northwest. Okay, I'm going to go back to the top, up high. Have the light to the north, and I'm going to bring it down and to the west, and then to the east. I mean, to the west, and this is to the east. Okay, I'm dyslexic. Okay, we'll see how that works.